Hi everybody, today we're going to talk about melting points. A melting point measurement is one of several techniques that organic chemists can use to determine the purity of a solid. It's the temperature at which a crystalline solid becomes a liquid at 1 atmosphere pressure. A pure solid has what we call a sharp melting point, which is generally a range less than 1 or 2 degrees C. The melting range itself is defined as the interval in degrees, beginning at the very first appearance of a droplet of liquid in the sample, and ending at the temperature at which the entire sample is melted. Impurities lower and broaden the range of the melting point. It just takes less energy to disrupt a crystal lattice when impurities are present. The impurities interfere with the weak forces that hold the crystal together. Here's ibuprofen in a capillary tube. The ibuprofen's been extracted from a tablet, and we're going to look at the melting point to determine whether or not the sample is pure. So on the right hand side, you see in the upper right, you see at just above 72 degrees some liquid droplets starting to form. So let's record that as our first melting temperature. And then at 73 we see some liquid starting to form very clearly, very visibly. At 74 degrees we see a slurry, and at 75 we see the entire sample is clear. So our melting range is 72 to 75. We look the value up in the Merck index and we see that the actual value is 75 to 77. So because the range is broader and the melting point's lower, we can conclude that our sample is not 100% pure. When you take a melting point and you have an unknown, you can get a rough approximation at first by putting your settings on a little higher than you normally would to go quickly through the melting point just to get an idea where it is. And then you want to do the next sample much more slowly, where you want to go degree by degree, starting at about 10 to 15 degrees before where the actual melting point is. And just as you saw before, going degree by degree will give you the best, most accurate information. Sample size is very important, and you want your sample to be around 1 millimeter. You don't want it to be quite as big as the two samples on the right, and not quite as small as the sample on the left. The sample in the middle is about the upper max. That's about 2 millimeters. You don't want it filled any more than 2 millimeters. The mixed melting point method is a simple way to help you determine an unknown. If you have an unknown compound and you've measured its melting point and you've determined that it's 120 to 121 degrees centigrade, and you want to find out what it is, well, what you can do is mix another compound in to the solid. You want to mix things very, very thoroughly, and you see in the literature, for instance, that urea has the same melting range. Cinnamic acid has the same melting range as your unknown. So if you mix urea and you run your melting point and you still get a range of 120 to 121, guess what? Your sample's urea. But if a range of 110 to 116, your sample is probably not urea. You should note that there is one unique mixture of two components in a solid that has a lower melting point than any of the other mixtures. That is a certain mole fraction, a certain proportion of A and B that has a lower melting point than any other mixture or proportion of A and B. In fact, that melting point is actually very sharp. It's actually just as sharp as often as that of the pure substance. This particular fraction of A and B, a particular mixture, that particular fraction, that's the eutectic mixture, and the melting point there is called the eutectic point. Okay, so let's look at a melting point diagram, which you guys are going to have to actually construct. And the two extremes of the melting range, the low and high temperatures, are shown for various mixtures of A and B. The upper curves indicate the temperature at which all the sample is melted. The lower curves indicate the temperature at which melting is observed to begin. With pure compounds, melting is sharp and without any range. This is shown at the left and right hand edges of the graph. If you begin with pure A, the melting point decreases as impurity B is added. At some point, a minimum temperature, or a eutectic, is reached, and the melting point begins to increase then to that of substance B. The vertical distance between the lower and upper curves represents the melting range. Okay, and your melting point diagram that you're going to obtain from your own data, as well as that of your classmates, looks more like the upper left. It's going to look more like the one in the upper left, and you're going to extrapolate, make some assumptions to determine your eutectic point with some limited data points. But you can do it, and make sure your solids are mixed really well. And also see in the Fessenden textbook, problem 2.4. So you should watch these two videos that I've got linked here. One of them is you only need to look at the first 54 seconds. It'll show you how to fill the capillary properly. And the second video has a lot of great info about melting points in general, how to do them, the principles behind them. Goes into a little more detail than we went into here, and also goes into the procedure. The specific procedure in that video and materials are a little bit different than what you'll be using, but their principles are exactly the same, and it's very important you watch that. The above links, as well as your manual and text, are also very useful in explaining potential experimental pitfalls. You should know all of these and what you should do about each of these 6 potential pitfalls before you come to lab. Thanks, and enjoy your melting point experiment.